Hello, Algebra 2. This video lesson about Chapter 7.2 is simply going to be me talking you through the chapter itself, 7.2, which is all about the properties of rational exponents. The one thing I will point out is the similarities to the properties of exponents that you learned in Chapter 6.1. Now we're just talking about a particular type of exponents, rational exponents. But there are very similar rules between Chapter 6.1, which should be familiar to you by now, and 7.2. So let's look at these example by example, starting with this first row here. The similar example. Well, if I've got two bases that match, a, and two different exponents on that matching base, I can add those two exponents, m and n. So here, matching threes, I can add the half to the 3 halves. I get 2, so in other words I have 3 squared, which becomes 9. Second example here, I've got a base with two exponents, one inside parens, one outside. I can multiply those exponents. We talked about that back in 6.1. Well, the same is true here. So I would do 2 times 3 halves, which becomes 6 halves, or in other words 3, and 4 to the third is 64. The next example here, and by the way, at any point if you want to hit the pause button and study these because I'm saying this too fast, by all means go ahead. There are a couple of ways I could treat this. In class, some of us talked about the idea that I could have just multiplied the 9 times the 4, and then I would have had 36 to the 1/2 power. Another way of looking at it, I could say that I've got 9 to the half, as I do here, and separately, or times, 4 to the half, as I have here. So I could look at it as the square root of 9, which is 3, and the square root of 4, which is 2, and I had 3 times 2, or in other words 6. Next example, when you've got a negative exponent. Well, similarly here I've got a negative rational exponent. All I do is pull everything that I have here, that 25 and the 1/2 power, I get rid of the negative sign and pull it down below, or to the other side of the dividing line. So notice all I really did was eliminate that negative sign by replacing it with a dividing line and putting everything that was left on the other side of the dividing line. Well, the square root of 25, or the 1/2 power of 25, is 5. There isn't really, so let me go back here, 3 to the 0 power, or 3 to the 0. Well, there isn't an irrational exponent version of 0. 0 everything over anything remains 0. So there's nothing different about this. 6.1's rule does apply to 7.2, but that's only because there really isn't any rational exponent with 0 in the numerator. Okay, so this example, if I've got the same base but two different exponents, the first term above and the second term in the denominator below, I can always do m minus n, or here I had 5 minus 3 back in chapter 6.1, or here I have 5 halves minus 1/2. 5 halves minus 1/2 is 4 halves, or 2. I've got 6 squared, which is 36. Last example. Both these items this fraction in parens to a power, I can separate the numerator from the denominator. Like here I change this to 2 to the third over 7 to the third. Well, similarly here I could do 8 to the 1/3. Well, I know what that is, that's 2. And on the bottom I could do 27 to the 1/3. I know what that is, that's 3, so I've got 2/3. Okay, let's put this to use. Starting with a here. I can add those exponents. 1/2 and 1/4 become 3/4, and that's really done. And the only reason it's done is because I don't know the 4th root of 5, and the 4th root of 125 doesn't really help me any. This is as simplified as this is going to get. But the second example I think goes a little farther, if I remember right. Okay, so I can separate this out. I separate the 8 from the 5, and so I've got 8 to the 1/2 squared and 5 to the 1/3 squared. Well, I can multiply the 1/2 times the 2 and get 1. And so I'm going to have 8 to the 1, and I can multiply the 5 times the 2 times the 1/3 and get 2/3. Well, 8 to the 1 is 8. And 5 to the 2/3, like I said before, above with that example, I don't know the cube root of 5. So this part's done. The only thing I want to caution you about, do not tell me, please, that this can be simplified to make 40 to the 2/3. Remember, this exponent 2/3 is only attached, only modifying the 5. It has nothing to do with the 8. C. I've got two different bases, both with the same power. I can put those together and do 2 times 3 to the 4th power. Well, in other words, that's 6 to the 4th power. Now on the outside, I've got negative 1/4. I can multiply 4 times negative 1/4, and I'll get negative 1. And 6 to the negative 1. Well, I'm not really done. 6 to the negative 1 is 1/6. Now I am done. The next example, that 1 I can subtract off the 1/3, and I get 7 to the 2/3. And this last example here, both these bases are both raised to the 1/3 power. So I could call it 12/4 to the 1/3 power. Well, I know what 12/4 is. That's 3. And 3 to the 1/3 power to the 2nd power, I can multiply the 1/3 times the 2. And I finish off with 3 to the 2/3 power, and there's no farther I can go with this one. The second example talks about very similar situations, but back here, all of these were rational exponents. Here they're all roots or radicals, but basically we're dealing with the same situation. Both of these are the 3rd root, so I can multiply the 4 times the 16 if I want to, and that makes 64, and the cube root of 64 is 4. Second example, both of these are to the 4th root. Well, I could do 162/2 if I wanted to, and make the whole thing to the 4th root. Well, that's 81 to the 4th root, and I know that the 4th root of 81 is 3. Okay, and sometimes, again, with a radical, it makes sense to break that radical apart. This is an example we didn't get to in class, I remember. So I don't know the cube root of 54, but inside of that there is a perfect cube. So if you can find a perfect cube inside, it's going to help you to factor that out. So separately, I've got the cube root of 27 and the cube root of 2. I know the cube root of 27, that's 3. But I don't know the cube root of 2, so I'm done if I call it this. Example B, and this one I think, well, I'm going to quickly go through this, but I don't know how often we're really going to use this. This is getting picky about the notion that you really ought not to have a radical in the denominator. And if you don't want one, then you're going to have to turn 4 into a perfect 5th power. Why? Because you're taking the 5th root. Well, you do know the 5th root of 32. That's how they came up with this 8. So they're multiplying times 8/8. This is an example I probably won't end up using a lot, but I'll just, well, in fact, I think what I'll do in the interest of time is I'll just quickly show you the answer and invite you to study this one in the textbook if you want to. I'm going to move on to example 4, when you're adding and subtracting these instead of multiplying them. So I've got 7 of these things called 6 to the 1/5, and then I add another 2 of these same things called 6 to the 1/5. Together they make 9 of them. I don't know what the 1/5 power of 6 is, but at least I've got 9 of them. Please don't call this, though, 54 to the 1/5, because again, the 1/5 only applies to the 6. It has nothing to do with the 9. Another example here, if I wanted to subtract these things, well, this is really the cube root is 16, or 16 to the 1/3 minus 2 to the 1/3, if I wanted to call it that. But in order to subtract, they've got to match. So let's see if I can do that. Factor out the 2 that would make them match. And the good news is I do know the cube root of 8. Cube root of 8 is 2. So I've got 2 of these things called the cube root of 2 minus 1 of those cube root of 2's. And so I've got 1 cube root of 2, or I can just call it cube root of 2. Example 5. All right, now it gets even more complicated. I'm doing the cube root of 125 y to the 6th. Separate the coefficient 125 from the variable. I can do the cube root of 125 because I know that's 5 to the 3rd power. Also, this y to the sixth. Well, there is 6 is a factor of, 6 is a multiple of 3. So I can factor out the y squared and the 5 to the third. Another way I tend to think of it is as tickets out. This y to the sixth. Well, for every set of 3, I can get one of these y's out. I've got 2 of these sets of 3, so I can get 2 y's out. Oops, didn't mean to highlight that, or that for that matter. Okay, here. This is the same situation as above here. Here I was taking cube root, this time I'm taking square root. But as a rational exponent, well, you might find that this actually makes more sense. I can multiply the 1/2 times each of the individual pieces. I know 9 to the 1/2. That's 3. The u, I had u squared to the 1/2. Well, 2 times 1/2, you're going to see is 1. And v to the 10th times 1/2. Well, that's going to be v to the 5th. So I've got 3, like I said, u to the 1, v to the 5. 4th root of x to the 4th over y to the 8th. I could separate the top and bottom. 4th root of x to the 4th, well, those 4's are going to cancel. On the top, I'm going to have just x. On the bottom, though, notice this. They don't cancel, but I've got 2 sets of 4. Now those 4's cancel. I pull y squared out, and I pull x out. And I end up with x over y squared. Example D. And we're now even more complicated. So let's parse this out here. Notice that 6 over 2 became 3. That's right here. The x over x to the 1/3 becomes 1 minus 1/3. The y to the 1/2 over nothing remains y to the 1/2. And there's nothing over z to the -5, but it's on the wrong side of the line. It's going to come up above and become z to the +5. So I end up with 3 x to the 2/3, that's 1 minus 1/3. Y to the 1/2, didn't have anything else involving y. Z to the +5. That one's done. Okay, I don't know if we're going to get all the way to example 7, but we are, at least in this video, going to get through example 6. Okay, as I said, you can, if you want, think of 5 as a ticket out. But that means if you have 5th roots. That doesn't mean you can take this 5 out. But I do have 5 sets of A. So, as this says, I'm factoring out perfect 5th powers. That's what I'm calling that ticket out concept. I've got 5 A's. I actually had 9 B's. Well, pull aside the 5 B's, the complete set, from the not quite complete set, the 4 B's. I had 13 C's. I had 2 complete sets plus another 3. Now, I can pull to the left the ones that I'm going to be able to factor out. So the complete sets, in other words, A5, B5, C10. And in the right, the ones that are going to have to stay inside that won't be able to get out. On the left, I'm going to have the A, the B, and the 2 C's, or in other words, C squared. On the right, I'm going to have the pieces that could not be factored out. And the last example that I think I'm going to be able to fit in this video is B. Cube root of x over y to the 7th. Well, again, this goes back to that notion they had before. You have to have, you're not supposed to have a denominator and a radical sign. I think in this case, I'm actually, once again, going to let you study that one yourself. So since I'm going to let you study B yourself, I'll just fast forward to the answer that you can see in the textbook for yourself. Go ahead and turn to that page if you want to understand this notion better. I'm realizing I'm coming to the end of my time, and I still wanted to show you example 7 as well as the word problem, so I'm going to make a separate short video to finish this off.